Hello, my name is Yuwei Zhang. I'm here to present my research toward unsupervised realistic visual question answering. The problem of realistic visual question answering, also referred as RVQA, aims at improving robustness of VQA systems to unanswerable questions, also referred as UQs in this slide. Lack of robustness to UQs will let VQA system choose an answer that is statistically most related with the question. And this can create safety hazards for indoor robots or assistance for the visually impaired or so many other applications. We argue that our VQA should first accept or reject the questions, and then answer those questions that are accepted. There are mainly three challenges of previous datasets. First, collecting unanswerable questions for training is expensive, and training on one type of UQs does not guarantee generalization to others. Second, prior datasets contain unrelated image and questions as UQs that are easy to reject. For example, the question can ask about something that does not exist in the image. Third, VQA datasets that support RVQA, such as VisWiz, are designed for a specific application domain, frequently containing images with few objects. In response to these challenges, we propose two candidate selection methods, clip-based and perturbation-based. For each of these methods, we propose to split them into two subsets, an easy version and a hard version. For clip-based, we first rank all questions for each image according to clip similarity score, and then choose the most similar ones as hard, and the most dissimilar ones as easy. For perturbation-based, we perturb the objects or attributes in the questions with semantic parsers. Finally, all those candidate questions are annotated by humans. We show some qualitative examples in this slide. Many questions have subtle mismatches with images, and thus require the model to have high-level understanding of image semantics. For example, for image question pair B, the model should understand whether the person is wearing the shoe or not. Compared to existing dataset, first, RGQA is built upon the test depth set of GQA, and it is only for evaluation purpose. Second, RGQA can be used to evaluate both VQA classification and UQ detection. Third, RGQA uses clip-based and perturbation-based methods to generate candidates, which make the dataset challenging. We further show the distribution plot of clip similarity score between images and questions for both previous datasets on the first row and our datasets on the second row. For clip-based and for clip-hard and PT-hard, we have a large overlap between answerable and unanswerable image question pairs, which make them challenging. Since our problem requires jointly solving two problems, VQA classification and UQ detection, we also propose a set of metrics based on ACC FPR curve. ACC refers to the proportion of AQs with correct VQA prediction and accepted as AQs. FPR refers to proportion of UQs falsely accepted as AQs. And then we propose three metrics according to ACC FPR curve to measure our model. We then propose three model-agnostic methods for unsupervised RVQA learning. Here, unsupervised means that the learning does not require annotated UQ for training. Random pairing will sample pseudo UQ for each image and train with binary cross-entropy loss. ROI mix-up further mixes ROI features of two images with a given proportion in order to increase the coverage of fine-grained mismatches. Finally, model ensembling further integrates the outputs from above two models. In this table, we compare recent VQA models using a popular OOD method that rejects questions by thresholding the highest prediction probability, referred as MSP. The results show that all VQA models are quite vulnerable to UQs. Furthermore, larger and more recent models such as WinVL, MDTER, and BLIP do not fare significantly better than smaller models. In this table, we further compare different RVQA methods with 3 backbones: BUTD, UNITER, and LXMERT. First, we show that post-hoc approaches such as ODIN and energy-based method do not help. Second, our proposed pseudo-UQ methods, including RP, MIX, and ENS, are effective. Third, our VQA approaches benefit from better VQA methods. LXMERT consistently outperforms BUTD and UNITER. Finally, training with diverse UQs is important. If we only train on hard UQs, the performance on easy UQs will be degraded. We also conduct the human evaluation on MTurk. Workers are assigned binary rejection tasks from a subset of our dataset. While ENS achieves human-level performance on easy sets, there is still a large gap on the hard sets. In conclusion, we studied the problem of RVQA, which aims to both reject UQs and answer AQs. We assembled the RGQA dataset using 2 approaches to generate candidate UQs for human annotation. A combination of pseudo-UQs, ROI mix-up, and model ensemble was then proposed for unsupervised training of RVQA models. Finally, experiments show that the resulting models outperform RVQA baselines. Comparison to human performance show that more research is needed for RVQA. Thank you for listening.